That,
My,
did
that's
your
my
daughter
daughter.
do that one too?
Yeah, I mean, she has a new one, which of a sacred datura and a sphinx moth, or not a sphinx moth, but a Manduca sexta moth, which it's not ready for prime time yet because she can't go to a fine printer and get it scanned. Before the lecture, before the lecture starts, I just downloaded a data set that I'll show you. So see if I can, so everybody can see that. So that's the graph of the COVID cases in Pima County. So you can see the curve does not look bent. If you want to look at,
Wow.
so we're up to 941.
I did not know it was that many.
And then there's deaths. I've played around with Maricopa County and I played around with Pima. I think if you look at Navajo County, which I haven't sort of subsetted yet, things look bad, but you can see, well, you see these deaths come in spurts, I guess, as they get reported.
Yeah.
So that's where we are. It's not a good situation.
No.
So let's see. Any questions about the homework before I go launch into the lecture? Whoops, that's not the homework. Is it? Oh yeah, it is. Any questions before we get going? So Zhao Ying had a fair statement about this. So she's used the delta method to give the standard deviation. Well, maybe to estimate the standard error, right? Because you're going to have to use, once the delta method is used, you're going to have in it the variance of R1, the variance of R2, the mean of R1, and the mean of R2, and you're going to use the sample means and the sample standard deviation, sample variances to get that. So it'll get you going. Okay, so here is
Dr. Joe, for the question 1, are we assuming that they follow a normal distribution, or are we supposed to find out because for the confidence interval?
Okay, so for the confidence interval, I'm letting you use it. So in part D, I'm saying use the normal distribution. So I'm saying in some sense that my data set is big enough so that so that the central limit theorem applies. And then the other thing is, let's see here. So somebody was worried about R1 is the distance to the object and R2 is a distance to the image. And so R1 has you'll see has a smaller standard deviation because I'm measuring a distance to an object. But if you look at a lens and there's a distance to an image, that's harder to measure. So I took more measurements of that. I mean, I simulated more measurements of that to sort of compensate what would actually happen.
Is there like a specific reference distribution we use for R1 and R2 for that data there?
No, you just you have to live with all the samples, right? I mean, I have a reference that I use to build it with, and I could if you send me an email, I'll secretly shake your hand with the numbers I put in there. But I'm just saying use the data and estimate the standard deviation of F. So the goal is, and I did something very similar to that with the lens data, right? I just took, the lens data also had a theta 1 and a theta 2, and I need to estimate theta 1 bar and theta 2 bar and the variance. And I just used the data to do that inside of the two terms that were used for the delta method. Does that help? Okay, oh, there's a question, there's a comment. Can I get to the comment? Where did it go? There. Okay, so Nathan wants to use the t-statistic. So if you want to use the t-statistic, then what you would really have to do is you would have to go to some strategy that was like the Welch-Satterthwaite theorem, and that creates a sort of an effective number of degrees of freedom with the t-statistic. And so you'd have to go back to that formula that we use for the two-sample t-distribution and modify it appropriately to do that. If you are keen on doing that sort of thing, then I think I worked out what that would be, and if you ask me for that, I can send you a link to that formula. Okay. No, oh, for R1 and R2. Oh, for R1 and R2, yeah, you can go ahead and use the t-statistics for those if you want to. Sure. Sorry, I guess I overthought that one. Oh, okay. So yeah, we'll do that. So we'll do that later. I actually haven't had a chance to look. Hello, Hamza. I haven't had a chance to look at the syllabus. Can we discuss it after class? Probably, yeah. So if everybody goes away, we'll talk about it after that. But I haven't. I'll have to look at the syllabus. Okay. Away we go. Whoops. So this one is a pretty packed lecture, and it puts an awful lot of stuff together that uses a lot of what we've done over the past 1.5 or nearly 2 semesters. And then so what the thing I wanted to get across to you is why is the chi-square distribution so ubiquitous from a theoretical perspective. So I'm going to review what likelihood ratio tests are and the nature of the likelihood and its properties in one dimension. Then Wilks was the person, the statistician, I guess, who created this chi-square framework that we use. Although Galton knew about it a long time before that in an informal sense. Wilks is the one to put it in this likelihood ratio testing framework. And then I'm going to use an example from blood bank data. I did some reading before class. There's a lot of concern given all the people who have compromised health that there's not enough blood coming into blood banks, and they're really after those who have had the corona virus or suffered from COVID-19 and have recovered, and so they have antibodies. I know that Tom Hanks is given his blood to use as antibody test. He sort of announced the other day. Okay, whoops, why did I do that? Okay, so the likelihood ratio test is used for composite hypotheses. So you have two sets, theta naught and theta 1, and they're disjoint, and their union is the entire parameter space. And we're going to look at situations where that parameter space is multidimensional, and it may not be an entire linear space, but it should be a subset of that, at least an open subset of that. And theta naught is a subspace. The other ways you see this is you can think of some linear transformation that acts on the parameters, and then the null hypothesis is that the linear transformation on the parameters is 0, and the alternative is that it's not 0. And so so if the rank of your linear transformation is k, that means that you're in some sense constricting k of the components, and that means that you have d minus k of them unconstricted if your parameter space has dimension d. So there's this relationship between the rank of k and the dimension of the subspace that associates with the null hypothesis. So to give a simple example of that, that should be if d is 3, and if you're right, the null hypothesis is that your second parameter is 0, and so the theta 1 and theta 3 are nuisance parameters, then you can write, there's a variety of ways of writing A, but here's one way to write A. So if you looked at A times theta 1, theta 2, theta 3, you would get theta 2 as 0. So the rank of A is 1, and the subspace that's determined by the null hypothesis is 2, right? You have any value for theta 1 and theta 3 are available to you. The one that we're going to look at later is we're going to look at the set of probability measures or probability distributions on a simplex. So PI through P1 through PD are a bunch of non-negative numbers that sum to 1. I guess I should have put they were non-negative. And then we're going to choose a vector pi. And the choice the choice H naught, where the vector you see is some prescribed vector pi, is called goodness of fit. And that's the example I'm going to do much later on. Okay, so for likelihood ratio test, the typical thing we do is we maximize the likelihood over the null hypothesis, and we maximize the likelihood over the entire space, and we look at that ratio. So that ratio will always be less than 1, right? Because we maximize over a larger space for the expression in the denominator, and so that has to be bigger. So the rejection region for an alpha level test is where that likelihood ratio is below some amount, and we're going to later see that that some amount is determined by a chi-square distribution. So lambda naught is chosen, so we're conservative in this sense, so that no matter what theta you pick in the null hypothesis space, if you look at the probability distribution under the parameter value theta, the likelihood ratio statistic for those data will be below lambda naught. That event has probability at most alpha. Okay, so I'll let theta hat naught be the parameter value that maximizes the likelihood when the null hypothesis, when you're in the space for the null hypothesis, and I'll just use theta hat to be the parameter value that maximizes the likelihood across the entire parameter space. So that's a little notation. Then we have a somewhat contracted, simplified notation for the likelihood ratio, right? We just have, we substitute the value for the supremum in the numerator, and so I get a theta hat naught of x, and then the same thing in the denominator. Now that's not exactly what I'm going to end up working with. What I'm going to do is I'm going to relate each of those quantities in the numerator and the denominator to the state of nature, and that'll allow me to use Taylor's theorem and the strong law of large numbers and the central limit theorem in a variety of ways to get what I need to do. So let me remind you of some of the properties of maximum likelihood estimators, at least in one dimension, and then we're going to soup that up to multiple dimensions. So psi naught is the true state of nature, which we almost never know, and theta hat is the maximum likelihood estimator based upon n observations from a simple random sample. So they're independent, identically distributed random variables, and whose distribution is parameterized by, takes on the parameter value psi naught. Then we know that consistency means that the maximum likelihood estimator converges to the true state of nature. Psi naught is as the number of observations increases, and that converges is in probability and a variety of other ways. And then asymptotic normality and efficiency are both contained in this statement. So if you have some technical assumptions, those technical assumptions are really what you need so that you can take two derivatives of the score function, the log of the likelihood function, and you can take some means of that and variances of that. If those things are good, then you take the difference between your data, theta hat n, and the state of nature. That converges to zero, so you'll see soon that the right thing to do is to expand that window by a fraction squared of n, and that window will stay a substantial size. The data will bounce around, but it'll converge in distribution as n goes to infinity to a normal random variable. So we've seen that before, and so we're going to again use that, but in a multidimensional setting in a few minutes. Okay, right. So that, oh yeah, so it converges with mean zero, and the variance is 1 over the Fisher information for one observation, evaluated at the state of nature. Okay, so we saw this before, and in the case of normal data and a two-sided hypothesis on the mean, and it gave us a hint about what we should do. So if I look at the mean is some value mu naught versus the mean is not that value, so it's a two-sided hypothesis, and my data are n independent normal random variables with mean mu and a known variance sigma squared, then to keep things sort of in this idea of state space or subspaces, I'll let theta be mu minus mu naught, so that the center is at theta equals to 0. So that we can change the hypothesis that h naught is theta equals 0 and h1 is theta not equal to 0, since we linearly shifted by an about mu naught. Okay, so the parameter space is one-dimensional, giving the value theta plus mu naught for the mean, right, shifting it back. And so the estimate for theta hat would be just to take the sample mean from the data and add mu naught to it. So theta is a single point 0, and theta, and so the maximum likelihood estimator for theta naught is 0 because it's the only point available to us. So then we stuffed that into the likelihood ratio, we maximized things, and we simplified the likelihood ratio, and we got this e to the minus n over 2 sigma naught squared times x bar minus mu naught squared. And so I isolated that expression in the exponential, and I can do that by taking logarithms, and that drops the exponential, and then I'll multiply through by -2, which will get rid of the 2 in the denominator, and the negative sign. And so what I'm left with is n over sigma naught squared times x bar minus mu naught squared. Okay, and then I'm just going to do some algebra on that. I'll put that n over sigma naught squared in the denominator, where it becomes sigma naught squared over n, and then I'll write everything as a square so that it becomes x bar minus mu naught divided by sigma naught over the square root of n. So under the null hypothesis, that expression in the parentheses is a standard normal random variable. And so if you square it, you get a chi-square 1 random variable. And so in this base case of 1 dimension normal data, then you see that that if I take -2 times the log of the likelihood, I get the z-score squared. And so that's a chi-square distribution of 1 degree of freedom, right? The square of a standard normal random variable is chi-square with 1 degree of freedom. So that sort of gives us a suggestion of the way we ought to go. Okay, so now multiple dimensions. I'm going to change bases so that I have an orthonormal basis, although actually I don't think I really ever use that on the parameter space psi. And then in that case, the first k of those will be 0. So I'll use the columns of A as a way to create basis. And so that theta naught is just the first k of the coordinates are 0. And then, so the dimension of that is d minus k, right? The remaining coordinates are unrestricted. And so I'll write theta superscript 0 to be the value in those k coordinates. And I'll write eta superscript 1 to be the values of the remaining d minus k coordinates. And so now my hypothesis becomes that theta superscript 0 is 0, right? The first k coordinates are 0, and then the alternative is that they're not 0. Okay, and so now I'm going to maximize just like I did in one dimension for the likelihood ratio, but I have to maximize under 2 circumstances, and it's multiple dimensions, so I'm going to have to take a gradient rather than just taking a derivative. So I'll let the superscript 0 under the gradient be the gradient with respect to the first k coordinates, and the superscript 1 be the, pardon me, the gradient with respect to the last d minus k coordinates. Okay, away we go. It's now time to do some maximization. So I'm going to have to maximize under the null hypothesis, maximize overall. Then I'm going to have to take those maximum values and stick them in the likelihood ratio statistic and see what happens. So that takes quite a few slides, 6 or 7 more slides to do all that stuff. So if I want, and I'm going to do some Taylor series approximations, and I'm going to use Slutsky's theorem and so on. So a lot is involved in the next few slides. So if I want the gradient with respect to theta 1 to be 0, that's the gradient 1 to be 0. That's a maximization over theta naught, and then I need the entire gradient, both the gradient on 0 and the gradient on 1 of the log of the entire likelihood function for both cases to be 0. So those are the 2 maximization criteria that I face in order to get this likelihood ratio test. And then, so in the same token, I have this Fisher information matrix. And so I'm going to reparameterize I'm going to relook at my parameter space using etas as the parameter space. And then I have on the upper left-hand corner, the Fisher information matrix for the parameters that are 0 under the null hypothesis. And in the lower right-hand corner, I have the Fisher information matrix for the parameters that are not 0, perhaps, under the null hypothesis. So that gives me the upper and lower diagonals of these things. And then I need the Fisher information matrix that's based upon the covariant or the mutual information with respect to the variables 0 and 1. So they'll involve, when we look at the log likelihood, the partial with respect to 2 different parameter values, one that comes out of eta naught and one that comes out of eta 1. Okay, so now I'm going to write a linear approximation about this, the true state of nature. So everything is going to come back to looking at this true state of nature. And I'm going to write eta for eta naught, eta 1, or those should be superscripts, eta super naught, eta super 1. Okay, so if I take the gradient and I just do a linear approximation, then I have the gradient evaluated at the place where I'm doing my Taylor series expansion around psi naught, and then I need the second order derivatives, since I have the first order derivatives in the nature of my gradient to begin with. So I use an H there to be those second order derivatives, and that's called the Hessian matrix. That's a Hessian matrix of all the possible second order derivatives. You apply that to the log likelihood function, and then that gives you a matrix of values, and then you multiply that by eta minus psi naught, and that gives you a vector of values. And so that is the, in some sense, the tangent plane or the tangent hyperplane approximation to the gradient of the log likelihood at this true state of nature psi naught. Okay, so now I want to substitute the maximum likelihood estimate in there. That is, I solve for the gradient of the log likelihood to be 0, and I'll substitute it in that equation and see what happens. So if you do that, if I look at the equation above, I have the gradient of the log likelihood evaluated eta hat n is approximately equal to the gradient of the log likelihood evaluated at psi naught times x. Oh, I should say the gradient of the log likelihood evaluated at eta hat n is 0. And so then, at the end, I have to put the eta at the end of the expression, and for that, I'll also substitute eta hat n in for eta, and then I get that the gradient of the log likelihood at the state of nature is approximately equal to this negative Hessian, right? I'm going to bring, one term is 0, so I'm going to bring the term on the left is 0, so I'm going to bring one of the terms over to the other side, say the Hessian term, and that gives me the negative sign. So it's negative the Hessian applied to the log likelihood, and that is a matrix which I apply to the vector, which is the maximum likelihood estimate minus the true state of nature. Okay, and then what I'm going to do with the left-hand expression, you remember that the score function has mean 0, and so and that score function, as we'll see on the next slide, is the sum of score functions for each of the individual observations. And since it has mean 0, it's something that I have a chance to use the central limit theorem on. So I'm going to do that. The terms on the right, the Hessian on the log likelihood, that doesn't have mean 0, but so I'm going to divide that through by n, because that'll set me up to use the law of large numbers on that matrix. And then in order to keep things even, since I multiplied through by 1 over the square root of n in front of the gradient of the log likelihood on the left, and 1 over n times the Hessian of the log likelihood in the middle, I have to multiply by the square root of n times that last term in order to keep the equation balanced. Okay, so we're going to work on the limiting distributions of the term on the left, and that involves the gradient of the log likelihood and the distribution of the Hessian, and then that'll give us a limiting distribution for the term on the right. And we've seen already this in one dimension. So in one dimension, that limit was converged to a normal random variable with mean 0, and the variance was 1 over the Fisher information. So something very similar to that's going to happen, but we have to do a little bit more work because we're in a world of multi-dimensions, and so we have matrices instead of numbers. Okay, so the random variables, the gradient of the log of f of xi given the true state of nature are independent. We're considering those cases where the xi's are independent observations, and they have mean 0. We learned that about score functions last semester. And the variance is the variance is psi naught, the Fisher information matrix, right? The Fisher information matrix at one level is described as the variance of that object. Okay, and so for the term on the left, it's 1 over the square root of n times the gradient of the log likelihood. I can write that gradient as a sum, right? So the likelihood is a product of f x1 given psi naught, f of x2 given psi naught, and so on. And then I would take the log of those things. That product of logs becomes the sum of those, the log of the sum, and then I take the gradient of that, which is a linear operation. So this 1 over the square root of n times the log likelihood, gradient of the log likelihood becomes 1 over the square root of n times the sum of the gradient of the log of the density functions. And that converges in distribution by the central limit theorem to a normal random variable with mean 0 and variance, whatever the variance is of the individual terms, which is the Fisher information evaluated at psi naught. But now that's a matrix. So I have a matrix valued central limit theorem. So it has variance and covariance structures that come out of the fact that we have a multi-parameter setting. Okay. So for the term on the right, we have this negative, the Hessian of the log. And again, I could write that as independent. Oh, so I know that. So I know that the terms in, I'm going to do the same thing with the log with the Hessian term that I did it with the gradient term. I could think as Hessian of the log of the independent observations f of xi, given the true state of nature. They're also independent and they have mean. Now mean, the Fisher information applied to psi naught. Remember the expected value of the second derivative in one dimension of the log of the density function was the information. So I'm going to use that fact. So that's 1 over n times the Hessian applied to the log likelihood. And again, I write the likelihood as a product, and then I take the log to make it a sum, and then I use the linearity of the Hessian of derivatives to write that as a sum. Negative 1 over n times the sum I goes from 1 to n of the Hessian applied to the log of each of those functions. And they're independent and they're identically distributed. And so the law of large numbers tells me that it converges to its mean, and its mean is just the Fisher information matrix. So it converges by the law of large numbers to the Fisher information matrix. Okay, so now I've taken care of both terms, and so the one term that I don't know about, I can relate its distribution because I know the distribution of the other terms. So the distribution of I of psi naught, right? I of psi naught was the limit of the terms that involve the Hessian on the right, and then the term that was left sitting there was the square root of n times eta hat minus psi naught. Converges to a normal random variable. And what is the variance of the object that I care about? So the object I care about is the square root of n eta hat x minus psi naught. And so I can write down that eta hat, square root of n times eta hat minus psi naught as the inverse of the matrix I applied to W, right? I just, right up here I have W equals to I psi naught times something. And so I just take the inverse matrix of both sides. And I get that that this expression involving the square root of n eta hat minus psi naught can be written as I of psi naught inverse times W. But we've worked in the past in 564 that if I have a matrix or a vector valued random variable and I multiply it by a matrix, then I can write the variances down by writing, by pre and post multiplying by the matrix which multiplies my vector valued normal random variable. So I'll get an I of psi naught inverse transpose. Well, the transpose is just extra because the Fisher information matrix is symmetric. So I really don't need the transpose, but there it is. And then the variance of W, and then I of psi naught inverse on the right, right? So the variance of a vector times a normal random variable is the variance of a matrix times a normal random vector is the matrix transpose times the variance of that normal random vector times the matrix. And I've just rewritten that identity there. But we already told you that, W has a variance structure that's the Fisher information matrix. So I put it in the middle. So now I have the Fisher information matrix with an inverse, and then I have it on its own, and then I have it again with its inverse. So I can pick the center matrix and multiply it either by the object on the left or the object on the right, you choose. And in either case, you'll get the identity matrix, and so it won't show up again in the multiplication. So the object that we're looking at in multiple dimensions is that the square root of n times eta hat of x minus psi naught has variance that's 1 over the Fisher information, covariance structure that's 1 over the Fisher information matrix. So that's very similar to what we had in the past. When we had in one dimension, it was just a number. So that variance was also just the variance of a random variable, real valued random variable, and its variance was 1 over the Fisher information matrix. I'm sorry, 1 over the Fisher information, excuse me. So that gets souped up to the matrix setting, and so now the variance is just the inverse of the Fisher information matrix. Okay, so I did all that under the entire parameter space. You could do it again if you want to, under the restrictions that go with theta naught. So that means you'll look at this restricted maximization where that's true. And so this last 2 lines on this slide are exactly the same as the 2 lines above them, except that I've appropriately specialized things. So every place you see an eta hat, you see an eta naught. Every place you see a Fisher information matrix I, you see the Fisher information matrix I1. So that's the Fisher information matrix applied to the variables that can vary because the first k are restricted by the null hypothesis to be 0. And I use the same identity with respect to a random variable W naught multiplied by a matrix to compute its variance structure. And so I'm left with I1, the inverse of the Fisher information matrix restricted to those values that can change. So that would be eta k plus 1 up to eta d. Okay. So now I want to get to where I show you why there is the chi-square distribution. So now I've done the work to maximize the values under the null and alternative hypotheses, or under the whole parameter space and under the null hypothesis. I've shown you that in those cases that the distributions are normally distributed, the square root of n times the maximum likelihood estimator, and subtracting from that the state of nature, those converge to multivariate normal distributions where the variance structure is the inverse of the Fisher information matrix. So now what I have to do is I have to substitute that back into the likelihood ratio test in order to figure out what the distribution is for the likelihood ratio for the likelihood ratio, and see that there's a chi-square distribution lurking back there. So in order to do that, you'll notice that in both cases I related the likelihood to the likelihood of the true state of nature. So in order to incorporate that into the analysis, I divide both the top and the bottom by the likelihood evaluated at psi naught. And then you'll see in a minute when I take -2 times the log, which was presaged to us by the example of the normal random variable in one dimension, then I get 4 terms, and I'm going to try to be careful with these 4 terms. So there's a negative sign. So if we look at 2 times the log of eta hat, that's in the denominator, so it should have a minus sign, but I multiplied by a minus sign, so it's positive. And then this -2 times the log of psi naught, that comes from the denominator to the denominator, so it should have a positive sign, but the negative sign in front of that gives me the negative. So I'm comparing, in this case, twice the log of eta hat, given the data x, and twice the log likelihood of psi naught. And that was exactly what I worked with to get the central limit theorem. And then I have 2 more terms that are very similar, but they're based upon comparing the maximum likelihood values that I got from looking at the estimate when the null hypothesis holds. Okay, so now I'm going to focus on the first 2 terms. For the first 2 terms, I'm not going to use just a first order Taylor approximation. I'm going to use a second order Taylor approximation. And I'm going to apply it not to the gradient of the log likelihood, but I'm going to apply it just to the log likelihood. So the first order term, if I expand around psi naught, the first order term is just going to be twice the gradient of the log likelihood. Oh, that should be evaluated at psi naught times eta hat minus psi naught. And that's 0, I guess, because at the true state of nature, I have to fix this a little bit, at the true state of nature, the log of the likelihood converges to 0 as n goes to infinity. That's not quite right, but that is 0 because we're at or near the true state of nature. And then for the second order terms, I now have the Hessian matrix again in the middle, but I have to pre and post multiply that by eta hat x minus the state of nature psi naught. So it's a transpose on the left and the vector on the right with the matrix of with the Hessian matrix in the middle. That's what the second order Taylor approximation looks like when you have a multidimensional setting. And there's a factor of a half because it's 1 over 2 factorial in disguise because we're the second term. And then I had a 2 in front of everything. So that's why that 2 is there to begin with. And so the 2 times a half goes away and I'm left with just this eta hat minus psi naught transpose times the Hessian applied to the likelihood times, should be to the log likelihood, times eta hat minus psi naught. Okay, and so we'll again use the law of large numbers on the likelihood term and the central limit theorem on those square root of n eta hat minus psi terms just like we did before. And then, so we're going to rewrite this quadratic expression in Taylor series as the square root of n times eta hat minus psi naught. So I put a square root of n on each of the eta hat minus psi naught terms, and then I compensate that with a 1 over n applied to the Hessian of the log likelihood. Because we've seen this before, we know exactly what happens. 1 over n times the Hessian of the log likelihood converges to the Fisher information matrix as n goes to infinity, so I'm good there. And the terms on the left converge to a normal distribution. We just showed this just a few minutes ago, and its variance matrix is I psi naught inverse. Okay, so now if you go back to 564, you'll notice that we can write down any non-negative definite quadratic expression as a U lambda U transpose, and the lambda is a diagonal matrix which has the eigenvalues of the Fisher information matrix, and U and U transpose are orthogonal matrices. Orthogonal means that the inverse is equal to the transpose. So so we did that in order to come up with the structure theorem for how to represent every multivariate normal random variable as a linear combination of independent standard normal random variables. And we'd use that to get the principal component analysis. So I'm going to reproduce that whole structure now with the Fisher information matrix. So, so I said lambda is a diagonal matrix of the non-negative eigenvalues of I psi naught. So those non-negative eigenvalues are actually going to be the information from each of the components. So if it's big, there's a lot of information, the variance is small. If it's small, there's not much information and the variance is big. And so I'm going to write down I psi naught to the minus 1/2, so pay attention to that, as U lambda to the minus 1/2 U transpose. And the way I get this lambda to the minus 1/2 is I take all those information values along the diagonal, lambda 1, lambda 2, lambda up down to lambda d, and then I know they're non-negative, so I can take their reciprocal and take their square root. So I'm left with, and that is in some sense the standard deviations that come with all of those components in the covariance structure. Okay, so now if I multiply, so I have to justify why I use I psi naught to the minus 1/2. So if you take I psi naught to the minus 1/2 and multiply it by I psi naught to the minus 1/2, if my notation is going to work for me, then I should have that be I psi naught to the minus 1. So let's walk through that. That's just a little bit of matrix algebra. So the definition of I psi naught to the minus 1/2 is U lambda to the minus 1/2 U transpose. So I write it twice. There's another U lambda to the minus 1/2 U transpose. But the U transpose U is 0 because U transpose is the same as U inverse. So those multiply to give the identity. And then I have a lambda to the minus 1/2 and a lambda to the minus 1/2. And so those are just going to be two diagonal matrices, identical diagonal matrices, with 1 over the square root of the lambda entries in each of them. And so when I multiply those two matrices together, I just get the matrix of lambda inverse. So I get U lambda to the minus 1 U transpose, and that is the inverse of the Fisher information matrix. So it justifies using the expression to the minus 1/2 power. Okay. So now I'm going to let Z be a vector of independent normal 0, 1 random variables. And by the structure theorem that I showed last semester, well, I guess first of all, I want to remind you that the covariance matrix is the identity matrix, right? So if you take any two of them that are different, their covariance is 0. So all the off-diagonal elements of my covariance matrix will be 0. And if you take an element on the diagonal, then you're just writing down the variance of that. And I said they were standard normal random variables, so the variance will be 1. So that says that the variance matrix of D independent standard normal random variables is the identity. Okay, so what is the variance of I psi naught to the minus 1/2? Okay, we've been here before. I can put the matrix in the front with a transpose. I didn't bother to write the transpose this time because the Fisher information matrix is symmetric. Then I have this identity matrix, right, because that's the variance of Z, the variance matrix for Z. Then I have an I psi to the minus 1/2 on the right. So the identity matrix goes away, and just like I showed you a second ago, the I psi naught to the minus 1/2 times I psi naught to the minus 1/2 is I psi naught to the minus 1. So that gives me the covariance matrix for Z tilde. So I can represent the covariance matrix for Z tilde, or I can represent Z tilde as I psi naught to the minus 1/2 times standard normal random variables. Okay, so we're finally almost to the end zone. I'm going to put the pieces together. So the first term was, this second order Taylor series expansion, the first term went away because the gradient is 0 or nearly so at the true state of nature. So then I'm left with those three terms. One is the square root of n times eta hat minus psi naught transpose. The second term is the Fisher, is the 1 over n times the Hessian of the log likelihood. And the last term is the repeat of the first term, square root of n eta hat minus psi naught. And I know that the first term can be represented as I psi naught to the minus 1/2 times Z transpose. The second term converges to the Fisher information matrix at the true state of nature. And the third term is just the same as the first term without the transpose, I psi naught to the minus 1/2 Z. Okay, so if I look at the first expression, the one with the transpose, if I have two matrices transpose, I can represent that as them multiplied in the reverse order. So that becomes Z transpose, and then I psi naught to the minus 1/2 transpose, I psi naught to the minus 1/2 times Z. But the I psi naught to the transpose on that is not necessary because that matrix is symmetric. And then I psi naught to the minus 1/2 times I psi naught to the minus 1/2. You add the exponents together and you're left with just the identity matrix, and so you're left with just Z transpose Z. So after 8 slides, I get the case that minus 2 times the log likelihood of eta hat minus the log likelihood at the true state of nature is just Z transpose Z. Now what is Z transpose Z? Well, it's just going to be Z1 squared plus Z2 squared plus Z3 squared up to ZD squared. So all that work collapses down to this remarkable formula, so that this is just really a chi-square matrix with D degrees of freedom. So you actually have to walk through this long process where you introduce the Fisher information matrix in the maximization procedure to find the maximum likelihood. It shows up again in substituting those factors in there in order to get the maximum likelihood. You represent the square root of n times eta hat x minus psi naught as some linear transformation of standard normal random variables. You put it all together, and all the factors that involve the Fisher information matrix disappear, and you're left with just a chi-square random variable. So it's sort of a remarkable simplification of things. Now, there was a denominator of that, and that denominator forced me to look at twice a log of eta naught the log, twice the log of the likelihood of, at eta naught minus the likelihood at psi naught. And then I have to base that upon eta naught x being the maximization of the log likelihood at theta naught. And if you thought that was complicated, that what I just went through, this is more complicated. The first order terms converge to an expression that involves this information matrix of the off-diagonal parts, where it involves parameters from the null hypothesis and parameters from the others. But if you do the work, it's about 10 or 15 lines of linear algebra. It cancels the last d minus k terms of z transpose z, and so you're left with that negative log the likelihood on the data converges in distribution to a chi-square random variable with k degrees of freedom. So now you have some idea of why the chi-square distribution is so ubiquitous with respect to these likelihood ratio tests. Okay, so now I'm going to use it, and you'll see that using it is going to be really, really simple compared to all this. So I'm going to look at goodness of fit, which is going to examine the case of a sequence of independent observations which can take one of d possible categories. And so I'm going to have, I'm going to look at a blood bank. There's 4 possible blood types, OA, B, and AB. And so the blood types at the blood bank should try to match the blood types of those individuals that need blood. And so the Red Cross announces what fraction of individuals from a national database have a given blood type. So I'm going to call those numbers pi 0, pi A, pi B, and pi AB. So those are the numbers that we have. And the question is, does the distribution of blood types in Tucson differ from the national database? So the actual fraction, let's say in Tucson, is P naught, PA, PB, and PAB. And so the question is, are they the same? That is, should the local blood bank alter its distribution of blood supply in order to accurately reflect local conditions? And so you will see this from time to time. If the blood bank, for some reason, has a low amount of blood of a certain type, it may call on particular people who are asked by the Red Cross and other blood donation agencies not to give until there's a need. So if you have type O blood, my father had type O blood, O negative in fact, he would get a phone call from time to time that says that we're in need of your blood. He was a universal donor and he would donate only at those times. Okay. So we want to place this assessment strategy in terms of formal hypothesis testing. And so pi is the postulated values of the probability. That is, the probability that a random individual is a member of the ith category is pi sub I. And we'll let the p's denote the possible states of nature, right? So this is a bunch of numbers on the simplex. They're non-negative, and they add up to 1. So that's the possible values that we could take. So the parameter space has d minus 1 free parameters, right? It's d-dimensional. There's pi 1 up to, or p1 up to pd. But once I've told you up to p minus 1, then pd is picked. Or the other way you can think about it is it's a d minus 1 dimensional hyperplane inside this d-dimensional space. So the parameter space has d minus 1 free parameters, right? Because once these are chosen, the remaining parameter value, once all but one or d minus 1 are chosen, the remaining parameter value is determined by the requirement that the sum be 1. Okay, so the dimension of the parameter space is d minus 1. Now the hypothesis is that all 4 by blood types in this particular case match the national average. So p sub I equals to pi sub I. The alternative is there's some difference. I don't know what it is, but some of them are different. We don't have the national database. So the parameter space for the null hypothesis is just a single point. Did my blood types in this particular example match the national database? So the dimension of the null hypothesis is 0. So that makes the number of degrees of freedom in my chi-square statistic easy. It's going to have the dimension of the whole parameter space, which is d minus 1, minus the dimension of the parameter space on the null hypothesis, which is 0. And d minus 1 minus 0 is d minus 1. Okay, now collect data. So the data are the categories for each of the n observations. And then I have to now do the work to figure out what the likelihood function looks like. So let's use the likelihood ratio criterion to create a test for the distribution of blood types in a given population. So here are some data, O, B, O, A, O, A, B. So 10 people come in and you take their blood types and here are the data. And so now I can write down the likelihood, right? They're independent observations. If I set things up carefully, if brothers and sisters come in, then I can't collect their data. So it's just going to be P sub O times P sub B times P sub O times 5 factors of P sub A times P sub O times P sub AB. So that's my likelihood. And I could write that as P sub O cubed because there are 3 O's, P sub A to the 5th because there are 5 A's, and then a P sub B to the 1st and a P sub AB to the 1st. So note that the likelihood has a factor of PI whenever an observation takes on the value I, and we have a word for that. We can say that the number of observations from each category is a sufficient statistic. So given the data X, then the only thing that matters is the number in each of these categories. So we've seen that those sums from each of these things be the sufficient statistic in this setting, which is really a multinomial setting. So that vector sufficient statistic is just the number of observations in each category. So now the likelihood function in general is just going to be P sub 1 to the N1 times P sub 2 to the N2, keep multiplying until you get P sub D to the ND. So that's my likelihood function, and it's now time to maximize it. So the likelihood ratio is the maximum value of the likelihood under the null hypothesis. That's easy because it's only 1 point, so that's going to be the pi's, and the maximum likelihood for any parameter value, so under the whole parameter space. So in this case, the numerator is the likelihood evaluated at pi because the null hypothesis is just a sample space of size. It's just a space of size 1 point. So there it is. There's a likelihood ratio, L of pi over n divided by L of p hat over n. Now I have to figure out p hat. I'm going to write it out. So it's a product of pi's in the numerator and a product of p hats in the denominator. And I'm going to write that as pi divided by p 1 hat to the n1 times pi divided by p hat d to the nd. That will make my algebra simpler soon. But I have to figure out what are the p hats. Okay, so the typical thing we did in the past is we took the log of the likelihood that we differentiated, we set it equal to 0, and away we went. In this case, so there it is. If I take the log likelihood, then I had a pi to the ni, a p1 to the n1, a p to the n2, and so on. So if I take the log, I get an n sub I times the log of p sub i's. And so, but not every value of p sub I is admissible. I have a restriction, so we can't just take the derivatives and set them equal to 0 and solve. We have to find the maximum under a constraint, and that constraint is that the sum of the pi's is 1. So this is exactly the setup that was built for Lagrange multipliers. So here's how Lagrange multipliers work. So think of those curves as level sets for the log likelihood function, right? They're dashed in blue. And then think of the constraint as this straight line. So that's where the sum is 1. Okay, and so if I look at the gradient, if I look at a function, if I look at the gradient of SP, then it's going to be a bunch of arrows that point perpendicularly to the line. So that's what I show in black arrows. And then if I look at the gradient of the log likelihood function, then it's going to be perpendicular to the dotted lines. And so that's what I show there. Now I cheat a little bit. Those lines should point in the same direction, but I have them in opposite directions just to make the picture a little clearer. And then at the maximum, those two lines will be either parallel or anti-parallel, and the ratio is called the Lagrange multiplier. So think about it this way. If you think of those dotted lines as a contour map, and then you think of the black line as a path, then what you're doing is you're walking along this path. And if you think about yourself hiking as you walk along the path, then uphill, then you could, if you look to your left or right, you might be looking uphill or downhill. If you want to look directly uphill, if you're walking uphill, you won't look 90 degrees, but you'll look some fraction smaller than 90 degrees. And that angle will get bigger and bigger. And then when you crest the hill right here, then you're at the top of the hill, and so then the direction uphill and you're in the direction downhill are the same, and so they're parallel in that particular case. So the Lagrange multiplier says that the gradient of the log likelihood is some constant multiple of the gradient of your constraint. So if I can write down the gradient as just each of these terms. Okay, in the first case, the log of the likelihood was a sum of ni log pi, and the likelihood is just a sum of pi's. So if I take the gradient, so for the log likelihood, I take the gradient, and I get, so microphone off, please, thank you. So if I take the gradient on the first one, I get an n sub 1, and then the log of p sub 1, p sub I, so I get an n sub 1 over p sub 1, n sub 2 over p sub 2, and so on. And I get the Lagrange multiplier times a bunch of ones, because that's just, it's p sub 1, p sub 2, p sub 3 for the terms. Okay, so that says that n sub I over p sub I hat is lambda, and I can solve for n sub I, so n sub I is lambda pi for all i's. Okay, now if I sum all those, then if I sum all the n sub i's, I get the total number of observations. I get lambda times the sum of the p sub i's, which have to be 1. And so I get that, so I wrote it on here. I get n is the sum of the n sub i's, the total number of observations is lambda times the sum of the p hats, but the sum of the p hats has to be 1. So n is just lambda. That's why I know that lambda is positive. And so I know that n sub I over p sub I is n, and p sub I hat, excuse me, is n sub I over n. So that was a lot of work to show you the obvious. The obvious is that your best estimate for p sub I is a fraction of your population that has that blood type. So the maximum likelihood estimate for the fraction of the population that has type A blood is just a fraction in your sample that have type A, and so on. So the estimate is just a fraction. So for the blood type, remember we had 3 that had O, 5 that had A, 1 that had B, and 1 that had AB. So those are my maximum likelihood estimators for each of those probabilities. Okay, now I have to substitute that back in to my likelihood function. So those p hats in the bottom get replaced by n1 over n, n2 over n, n3 over n, up to nd over n. And then I'm going to now move this to the typical way that you have seen chi-square tests if you've seen them in the past. And I do that by taking the ends of the denominator and moving it to the numerator. So now I have an n pi 1 over n1 to the power n1 up to an n pi d divided by nd to the power nd. So now that's just a little bit of algebra to get it to something that we've seen more frequently. So I'll let capital N be the random vector of the number of observations that occur in each category, right? That's my sufficient statistic in order to do this likelihood. So then the null hypothesis, when the null hypothesis is true, -2, so I have to substitute the values back into the log likelihood. -2 times the log of n is -2 times the sum I goes from 1 to d of ni times the log of n pi I over ni, right? So that's just me taking the log of the likelihood of that expression at the top of the page. And then the typical thing we do is we wipe out the minus sign and get a positive sign, and then we take the log function and we write its reciprocal, right? This reciprocal of the log. The log of reciprocal is the same as the log of the original expression. And we know from the theory that we have that it has a chi-square distribution with d minus 1 degrees of freedom. Okay, the typical thing that you see is not n sub I, but O sub I for likelihood ratio test. And the O is to remind you that's the observed occurrences of I. And the typical thing is you don't see n pi I, but you would say if the null hypothesis held perfectly, the expected number of observations I would see is just pi of I is just the probability of a Bernoulli trial, and there are n trials, and so the expected number of successes in n Bernoulli trials where the probability of success for each case is pi I. So that's the expected number of occurrences of I given by the null hypothesis. So then I just rewrote that statistic replacing n pi I with E and capital N with O. So they get -2 times the log likelihood given the observations is 2 times the sum of OI log OI over EI, okay? And that is called the G-squared statistic. It's not the one that you see so often. So the traditional method, for goodness of fit, instead uses the G-squared, instead of the G-squared statistic, this what is now called the chi-square statistic. This chi-square statistic is really old. It was created by Galton. Galton did not know anything about likelihood ratios. And so what he has is exactly this quadratic expression, quadratic approximation to O log of OI over EI that we used, in fact, to create the limit. So Wilks may have been inspired by Galton in order to figure out that the quadratic approximation is where everything is. So in either case, the p-value is the probability that this chi-square random variable takes on a value greater than the test statistic. Okay, so let's look at the situation nationally. The Red Cross recommends that blood banks maintain 44% type O, 42% type A, 10% type B, and 4% type AB. You suspect that the distribution in Tucson is not the same, and so here's your null hypothesis. Just copying down the 44, 42, 10, and 4% as the probabilities of each of these occurrences. And then the alternative hypothesis is one of those PIs is not equal to what I wrote above. Something is different about Tucson. Okay, so then you observe 400 people in Tucson who give blood, and you arrange things so they're independent observations. 228 have type O, 124 have type A, 40 have type B, and 8 have type AB. And so I just put those numbers in this table at the bottom of the slide. Then the expected number is just going to be what would happen if things were solved perfectly. So with 400 observations, I multiply 400 times 0.44, and I get an expected number. So that gives me this table. So 0.44 times 400 is 176, 0.42 times 400 is 168, 0.10 times 400 is 40, and 0.04 times 400 is 16. So that would be exactly the number of observations I get if we match the distribution nationally perfectly. Now, you know there's going to be some fluctuations that differ from the exact expectation. The question, are those fluctuations due to sort of random occurrences, or are there something systematic? That is, the number of people with type O blood in Tucson is higher, but is it really higher enough to matter? The type B blood match perfectly. Okay, so chi-square test handles all that for you. So you just write CHISQ test, and then you put in the numbers, and then you put in the probability of those observations, 0.44, 0.42, 0.10, and 0.04, and it just does it for you. So it says a chi-square test for the given probabilities. There are your data. Chi-squared is 30.844. The number of degrees of freedom is 3, right? Because there are 4 categories, but there's one constraint because the sum has to be 1, and so the degrees of freedom is 3, and the p-value is 9 times 10 to the minus 7. So it's very, very low, and so blood types are just different in Tucson and the rest of the country, right? The degrees of freedom is 4 minus 1. So the p-value is very low, and the distribution of blood types in Tucson is very unlikely to be the same as the national distribution. So now you have to make a test. So one of the things I suggest you do is just compute this chi-square statistic by hand, just so you get used to how it works. That is, you write a bunch of O's minus E squareds over E's, and then add them up and see that you get 30.88 or close to it, and you'll have some round off error. Okay, one of the ways that we like to show what is going on in the chi-square statistic is something that's called a hanging chi-gram. And that allows you to show, gives a visualization of where things are different. So this plot, in some sense, does what is called, with respect to these goodness of fit things, the residual. The residual is the square root of the entries inside of the chi-square statistic. So you take O minus EI, so that's the variance of what's observed from what's expected. So that number will be positive. They're more observed than expected. And you divide it through by the square root of the number expected. So that sort of normalizes it to give it something that is equal to what you expect. And this will have approximately a normal distribution with approximately a standard normal distribution, and the null hypothesis is true. So those numbers can be positive or negative. So I called them the residuals, and then you could just make a bar plot and a name. And so here's the bar plot. And so you can show from this, if you wanted to show, let's say, the person that ran the blood bank, why things are different from Tucson, then oh, so we never, okay. I guess if you encounter the case where E was 0, I guess I got asked, then then there would be no point in including it in the data. That is, you have no chance to observe it. So you can't have extra, I guess you can't have extra categories with no possibility for observations for this to work. Right, that was the, I guess, the question. Okay. So if you show this to the director of the blood bank, you go, look, we're at least 3 standard deviations above what the rest of the country has with respect to type O, and we're at least 3 standard deviations below what we expect for type A. So we really need to keep our type O amounts high, and our type A amounts, we don't have to worry about so much. D and AB, they're much smaller numbers, but I normalized it so you can see that AB is a couple standard deviations below the mean, but it's only based upon a handful of observations, so that number is not as reliable as the other 2. So that's a way to present to a person who's trying to just get a sense of the summary of the data, what the output is from a chi-square distribution. I have a tendency to do this quite a bit. I was working, I mentioned this work before, with geneticists, and they were looking at the range of where mutations were that caused genetic epilepsies. And so I would divide the protein with the genetic epilepsies as they asked me to, and then my null hypothesis, and then I would have a healthy population which would give me an expected number of mutations each of the ranges, and then I had an observed population, and I would create a hanging chi-gram to show you where the children that had epilepsy had an enrichment of observed mutations, and then places where it was depressed were places where mutations that were the source of a genetic epilepsy were not so common. That gave them sort of insight into what was going on. We ended up not displaying that with respect to the paper, but it helped them sort of sort things out. Okay, so the question was, I'll get to this sort of stuff next time. What does it tell us about that requires further examination? So if you look at the residuals right here, so each of these contributions to the chi-square statistic are obtained by squaring these values here. So if you want to examine where the null hypothesis fails, or why you reject the null hypothesis, then informally you would look at the size of these chi-square, and they'd say that's where the situation has a tendency to break the norm, right? So it's the overabundance of O and the underabundance of A that lead to me rejecting the null hypothesis. So I hope that answers your question. So this was a very long talk today. I had a very theoretical side where we tried to understand, or I tried to get you to understand sort of all the windy road that gets you to the simple expression that the log likelihood is just the sum of the squares of normal random variables. That is a lot of work from a theoretical perspective, but you've now been doing the theory of probability and statistics for nearly 8 months, and so you guys can handle, at least after you review it, a fairly intricate argument that gets you to this. And now at least you don't feel like, at least I don't feel like I'm using the chi-square statistic blindly. And if you want to do sort of analyses like Paul suggests, then you have a tendency to know, if you know where the chi-square statistic comes from, you have a tendency to know what departures from it mean. Okay, so that's a long lecture, and all I have to say today, unless there's another question. Okay, so I'll see you guys Thursday, and then one of you wanted to talk to me after class. So I may what I do. Yes, what I'm going to do is I'm going to stop the recording and end the meeting, and then I'll open the meeting back up, and you and I can get back on there, so I can stop the recording.
I have one question before you do that, Joe. So I started watching Ken Burns' documentary on the gene, and I was curious whether you had any participation in it.
No, but so I know how well you missed it. So they mentioned Wendy, what's her last name? Wendy Chang quite a bit.
Uh-huh.
And she had a child that had a genetic disease, which they didn't describe.
Right.
And she lost her child. And so she became interested in the genetics of rare disease. So that is hauntingly similar to what I dealt with. So the guy that I work with, his daughter died from a genetic epilepsy. And so,
wow.
And so we are now, and so we did exactly, so all the things that you saw in that movie were true. That is, the parents created this national structure. They built for us the databases. They got the genetic sequencing for 3 different types of, well, let's see, in one genetic epilepsy, we got the data from a clinic in Japan. One epilepsy we got from crowdsourcing with families, and one epilepsy, somebody discovered us and gave us a database of about 100 children. Now there are four different kinds of mutations in sodium channels that can cause epilepsy. 3 of them are well studied. The 4th one, almost nothing is known about. They don't even know if that channel is inhibitory or excitatory, right? So does it slow down the operation of the firing of these ion channels, or speed it up? That's not even known yet. And one thing you can think about in terms of brain health, and I had this discussion with my daughter yesterday, is the brain has to have sort of an unstable equilibrium. If you have this stable equilibrium, that's really a seizure state. It has to be an unstable equilibrium, or else you can't learn.
Right.
On the one hand. On the other hand, okay, so the brain is really this very tightly orchestrated issue of inhibitory and excitatory activities that have to stay in balance in such a way that it allows you to learn.
Right.
If the inhibitory part takes over, that's called death. If the excitatory part takes over, that's a seizure. So that's a simpler version of this, and she's trying to get to the bottom of how that all balances out for her dissertation. But so no, I didn't have anything to do with the Ken Burns special, but it was hauntingly similar to the types of things that I've sort of been around.
Wow. Yeah, it's incredible. We really enjoyed it.
So there you go. Any other questions before I disappear for the day? Okay. Well, thanks for listening.
Thanks, Joe.
So I'll be back in a minute, Hamza.
Thank you.